Welcome to Softly Curious. This space is created to help you slow down, soften your thoughts, and gently move toward rest. You do not need to concentrate or remember every detail. You can simply listen, allowing the ideas to pass through quietly, like distant lights seen through a window at night. While your body relaxes, your mind can wander calmly through a subject that feels familiar, yet is far more mysterious than it first appears. Tonight, we are exploring numbers. Numbers are everywhere. They shape our days, measure our lives, and quietly organize the world around us. We wake up to numbers on clocks, follow numbers on screens, and make decisions based on numbers without questioning their presence. They feel natural, almost inevitable. But numbers, as we understand them today, are not a fundamental part of nature. They are a human invention, developed slowly, shaped by need, and refined over thousands of years. For most of human history, people lived without precise numbers. Early humans did not count days, measure distances, or label quantities with exact values. Their world was structured by experience rather than calculation. Things were near or far, few or many, safe or dangerous. This way of thinking was not primitive. It was efficient. It matched the demands of survival. When a group of hunters observed animals in the distance, the exact number mattered far less than the situation itself. Were there enough animals to make the effort worthwhile? Were there too many to approach safely? Precision would not improve the outcome. Judgment would. The human brain evolved to recognize patterns, movement, and relative amounts long before it learned to count. Anthropologists have found evidence of this way of thinking in early human languages. Some cultures developed number words only for one, two, and then a general term similar to many. Beyond that point, numbers were unnecessary. This was not a limitation of intelligence. It was a reflection of environment and lifestyle. The brain creates tools when reality demands them, not before. The earliest forms of counting were physical rather than abstract. Fingers became the first measuring system. 10 fingers offered a natural structure, which explains why base 10 systems appear in so many unrelated cultures. In some regions, people counted using both fingers and toes, leading to base 20 systems. Even today, traces of these early choices remain embedded in language, tradition, and measurement. Before written numbers existed, humans relied on memory and simple marks. Notches carved into wood or bone served as reminders rather than calculations. One of the most famous examples is the Ishango bone, discovered near the headwaters of the Nile River. Dating back more than 20,000 years, the bone contains a series of carefully carved notches arranged in distinct groups. Some researchers believe it was used to track lunar cycles. Others suggest it recorded quantities or patterns. Regardless of its exact purpose, the Ishango bone represents an important moment. It shows humans attempting to move quantity out of the mind and into the physical world. This transition changed human life in subtle but powerful ways. Once quantities could be recorded externally, they no longer depended entirely on memory. Numbers could be shared, checked, and passed on. They could survive the death of the person who created them. This allowed information to accumulate across generations. Numbers became tools for remembering, long before they became tools for thinking. As societies grew larger, the need for numbers increased. Agriculture introduced new pressures. Farmers needed to know when to plant and when to harvest. Surplus had to be stored, divided, and protected. Trade required fairness and consistency. Ownership required records. These needs pushed numbers from the background into daily life. In ancient Mesopotamia, numbers began to appear regularly on clay tablets. These were not mathematical texts in the modern sense. They were practical records, lists of grain, livestock, labor, and debt. Numbers entered written history quietly, as accounting. The earliest written numbers were not about curiosity or beauty. They were about control and survival. The Sumerians, living between the Tigris and Euphrates rivers, developed one of the most influential number systems in history. They used a base 60 system, a choice that still shapes our lives today. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. These divisions feel natural, but they are inherited habits, not universal truths. 60 was chosen because it is highly divisible, making it practical for trade and measurement. What began as convenience became structure. At this stage, numbers were still tied closely to physical objects. A number meant something only when attached to sheep, jars, or days. Abstract numbers, numbers without objects, felt uncomfortable. This discomfort explains why 0 took so long to be accepted. 0 represents absence. Early societies struggled to see absence as something worth naming. Roman numerals, for example, had no symbol for 0. They could represent quantities, but not nothing. This limitation made complex calculations difficult. It also shaped how Romans thought about numbers themselves. Without 0, there was no true place value system. Mathematics remained constrained. 0 was formalized much later in India, where mathematicians began treating it as a number rather than a placeholder. This shift changed everything. 0 allowed numbers to expand infinitely and contract back to nothing. It enabled negative numbers, large calculations, and abstract thinking. Without 0, modern mathematics would not exist. When 0 traveled west through Arabic scholars and reached medieval Europe, it was met with suspicion. Some believed it was dangerous. Others thought it encouraged fraud. A symbol representing nothing, yet capable of changing everything around it, felt unsettling. But over time, its usefulness became undeniable. 0 quietly became one of the most powerful ideas humans ever invented. Another number that reshaped human understanding is pi. Pi does not count objects, it describes a relationship. Specifically, it expresses the ratio between a circle's circumference and its diameter. No matter the size of the circle, this ratio remains constant. Pi never ends. It cannot be written fully. Its digits continue endlessly without repeating. This made pi both fascinating and unsettling to early thinkers. Ancient Egyptians and Babylonians worked with approximations of pi long before understanding its full nature. They did not need perfection. They needed usefulness. Even today, pi is usually rounded and simplified. Its true value remains unreachable, reminding us that some numbers describe ideas rather than quantities. Numbers slowly moved from being tools of record to tools of understanding. They began to influence how humans thought about time, space, and the world around them. Not all at once, not deliberately, but quietly, step by step, as numbers became harder to separate from everyday life. As numbers became more stable and more widely used, they began to do something unexpected. They did not simply describe the world. They started to shape how humans thought about it. Once a society adopts a way of counting, measuring, and recording, that system quietly influences perception itself. Numbers stop being tools and begin to feel like structure. Different civilizations developed different ways of organizing numbers, and these choices were never random. They reflected environment, culture, and daily needs. While base 10 systems appeared widely because of the human body, they were far from universal. In parts of ancient Mesoamerica, for example, counting systems were built around 20. The Maya used a base 20 system that aligned naturally with fingers and toes combined. Their calendars, architecture, and astronomical calculations were shaped by this choice. In contrast, ancient Egyptian mathematics focused heavily on practicality. Egyptian scribes used numbers primarily for construction, agriculture, and taxation. Their system was based on powers of 10, but without a place value system like the one we use today. Each power of 10 had its own symbol. This made large numbers possible but calculations slow. Precision mattered, but efficiency mattered more. Meanwhile, in Mesopotamia, the base 60 system continued to spread. Its influence extended beyond accounting into astronomy and geometry. Babylonian astronomers divided the sky into regular sections, tracking planetary motion with remarkable accuracy. They did not know modern physics, but their numerical systems allowed them to predict celestial events reliably. Numbers became a bridge between observation and expectation. As numerical systems spread through trade and conquest, they encountered each other. This created confusion, resistance, and eventually adaptation. Numbers were no longer just local tools. They became shared languages. But like any language, they carried accents, assumptions, and limitations. One of the most important developments in numerical thinking was the introduction of place value. Place value allows a single symbol to represent different quantities depending on its position. This idea feels obvious today, but it was revolutionary. Without place value, numbers grow bulky and calculations become difficult. With it, numbers become flexible and powerful. Place value systems depend on zero. Without zero, there is no empty position, no way to distinguish between 10 and 100 cleanly. This is why the formal acceptance of zero marks a turning point in human thought. It allowed numbers to become abstract, detached from physical objects. The journey of zero is a story of resistance. In ancient India, mathematicians such as Brahmagupta began to treat zero as a number with its own rules. Zero could be added, subtracted, and used in equations. This was not merely symbolic. It changed how numbers behaved. Through Islamic scholars, this understanding traveled west. Figures like Al-Khwarizmi helped formalize arithmetic using Hindu-Arabic numerals. His works introduced structured methods for calculation that would later influence European mathematics. The word algorithm itself comes from his name, a quiet reminder of how deeply numbers and human systems are intertwined. When these ideas reached Europe, they clashed with older traditions. Roman numerals were deeply embedded in culture and authority. Switching to a new numerical system felt disruptive and even threatening. In some regions, the use of Hindu-Arabic numerals was restricted or discouraged. Merchants were accused of manipulation. Numbers, once trusted, suddenly seemed suspicious. Over time, practicality won. Calculations became faster. Record-keeping improved. Science accelerated. Numbers proved their usefulness, and resistance faded. But the memory of that discomfort remained. Even today, new numerical systems often meet skepticism before acceptance. As numerical thinking matured, people began to notice that numbers did not all behave in the same way. Some fit neatly into everyday counting, while others resisted simplification. Prime numbers were among the first to attract attention. These numbers, divisible only by 1 and themselves, appeared irregular and unpredictable. Ancient Greek mathematicians, including Euclid, studied them closely. Euclid demonstrated that prime numbers never end, revealing that even the simplest act of counting hides an infinite structure. This idea was unsettling. It suggested that numbers were not just tools humans used, but a vast territory humans had only begun to explore. Other numbers challenged intuition even more directly. The discovery that some quantities could not be expressed as fractions disrupted long-held beliefs. The square root of 2, for example, could not be written as a ratio of whole numbers, a realization that deeply troubled followers of Pythagoras, who believed numerical harmony governed the universe. Pi belongs to this same family of resistant numbers. Though it arises from something as ordinary as a circle, pi never resolves into a clean fraction and never ends. From ancient Egypt to the work of Archimedes, humans relied on approximations of pi, accepting usefulness over perfection. These numbers quietly taught an important lesson. Some truths can be approached, but never fully captured. As mathematics moved further away from physical objects, numbers became increasingly abstract. Negative numbers, once dismissed as meaningless, gained acceptance through practical needs like debt and direction. Later, complex numbers involving the square root of -1 were introduced and initially labeled imaginary. Over time, they proved essential in physics, engineering, and modern technology. Meanwhile, everyday life continued to attach meaning to familiar numbers. 7, 9, 13, 28, 12, and 60 gained cultural weight through calendars, music, architecture, and natural cycles. Gradually, numbers stopped feeling like human inventions and began to feel like the fabric of reality itself. Yet beneath that familiarity, they remain shaped by history, necessity, and belief, quietly influencing how the world is measured, understood, and lived. When people hear that numbers appear in nature, it often sounds poetic, almost metaphorical. But the connection between numbers and the natural world is not a metaphor at all. It is observable, measurable, and repeatable. What makes it fascinating is not that nature uses mathematics, but that natural processes consistently produce patterns that humans later describe using numbers. The numbers come last. The behavior comes first. Nature does not count. A tree does not decide how many leaves to grow. A shell does not calculate its curve. A storm does not measure its own rotation. Instead, natural systems follow simple rules related to growth, energy, balance, and survival. When these rules repeat over time, patterns emerge. When patterns repeat, humans recognize them. And when humans recognize them, they assign numbers. One of the clearest places where this becomes visible is in plants. Leaves rarely grow randomly along a stem. In many species, leaves follow specific arrangements that reduce shadowing and maximize exposure to sunlight. This arrangement is known as phyllotaxis, though plants themselves do not follow formulas. They grow in ways that allow light, water, and nutrients to be distributed efficiently. If you look closely at sunflowers, pine cones, pineapples, or certain cacti, you may notice spiral patterns moving in opposite directions. These spirals often occur in specific pairs of numbers. One spiral may move clockwise, another counterclockwise. The counts are not chosen for beauty. They arise naturally from growth processes that minimize overlap and maximize space. What matters is not that the numbers are exact, but that the relationships remain stable. Nature prefers consistency over precision. A sunflower does not aim for a perfect pattern. It grows outward, adding new seeds where space allows. The result happens to produce repeating numerical relationships that humans later identify. This same principle appears in shells. The spiral of a nautilus shell grows larger with each term, but its shape remains similar. This kind of growth allows the organism to increase in size without changing its basic structure. The shell does not know its own proportions. It simply follows a rule: grow, expand, and maintain balance. These patterns are not limited to plants and shells. They appear in hurricanes, galaxies, and even human fingerprints. In each case, the underlying process is the same. Growth follows constraints. Constraints produce repetition. Repetition creates patterns that can be described numerically. Animals interact with numbers in a different way. While animals do not perform arithmetic, many species can distinguish between quantities. This ability is known as numerosity perception. It allows an animal to tell the difference between more and less without counting individual items. Studies have shown that birds, fish, and primates can reliably distinguish between small quantities, usually up to 3 or 4. Beyond that, accuracy drops. This limitation is not a failure. It reflects how the brain evolved. For survival, an animal does not need exact numbers. It needs fast decisions. A bird choosing between 2 food sources does not need to know whether one contains 5 seeds and the other contains 6. It needs to know which one contains more. The same applies to predators, assessing the size of a rival group. Quantity matters, but precision does not. This approximate number sense exists in humans as well. Even without counting, people can instantly recognize small quantities. This ability is called subitizing. It allows the brain to process small numbers quickly and without effort. Larger numbers require counting or estimation. What is interesting is that this ability appears early in life. Infants who cannot yet speak can still distinguish between small quantities. This suggests that numerical intuition predates language. It is built into perception itself. Nature also favors ratios over absolute values. Many natural processes depend not on how much of something exists, but on how it relates to something else. Growth rates, spacing, and timing often depend on proportional relationships. Consider the spacing of leaves along a stem. If leaves grow too close together, they block light. If they grow too far apart, space is wasted. The optimal spacing depends on relative angles and distances, not fixed numbers. This is why ratios matter more than counts. The same logic applies to animal movement. Schools of fish and flocks of birds maintain relative distances between individuals. These distances change depending on speed, direction, and threat level. There is no fixed number of units. There is only balance. Even the human body follows this logic. Heart rhythms, breathing cycles, and walking patterns depend on ratios and timing rather than exact counts. The body adjusts continuously, responding to conditions rather than following rigid numerical rules. One of the most influential natural cycles observed by humans is the lunar cycle. The moon takes approximately 29.5 days to complete its phases. This number is not neat. It does not divide cleanly. But early humans did not need perfection. They needed regularity. Over time, this cycle was simplified. Many early calendars rounded the lunar month to 28 days, creating systems of weeks and rituals tied to observable changes in the sky. These calendars were not accurate in the modern sense, but they were reliable enough to organize life. The importance of the moon extended beyond timekeeping. Its phases influenced tides, animal behavior, and agricultural planning. By observing repetition, humans learned to anticipate change. Numbers emerged as tools to track these rhythms. The sky offered humans one of the earliest and clearest experiences of numerical regularity. Long before telescopes or equations, ancient observers noticed that certain lights in the sky moved differently from the rest. Against the seemingly fixed background of stars, planets wandered in repeating paths. These movements were not simple, but they were consistent enough to be recognized over time. By carefully watching and remembering positions, early observers began to notice cycles. Astronomy became one of the first fields where numbers truly mattered, not because the sky demanded mathematics, but because prediction depended on memory. To anticipate an eclipse or the return of a planet, past observations had to be recorded, compared, and aligned. Counting days and tracking intervals slowly turned observation into expectation. Numbers entered astronomy as a practical necessity, not as an abstract ideal. Seasons added another layer of numerical structure to human life. The length of the year, though slightly irregular, provided a long-term rhythm that shaped migration, agriculture, and survival. Early calendars struggled to reconcile the lunar month with the solar year. Months did not fit neatly into years, and this mismatch forced societies to adjust. Intercalary days and months were added, removed, and revised, creating new systems that balanced accuracy with usefulness. What all of these examples share is not numerical perfection, but adaptation. Humans observed natural rhythms, simplified what they saw, and created numerical frameworks that worked well enough to guide behavior. These systems did not capture nature exactly. Instead, they translated complex processes into manageable forms. In doing so, numbers reflected nature, but they also changed how nature was understood. As numbers became linked to natural phenomena, they began to carry authority. A pattern that could be counted felt dependable. A cycle that could be measured felt trustworthy. Numbers offered a sense of stability in a world filled with uncertainty. They created the impression that nature could be understood, anticipated, and perhaps controlled. Yet nature consistently resisted exactness. Measurements varied slightly. Cycles drifted over time. Growth patterns shifted with temperature, resources, and chance. Even when these variations were small, they revealed an important truth. Numbers describe tendencies, not guarantees. They summarize behavior, but they do not eliminate unpredictability. This lesson remains just as relevant today. Weather models rely heavily on numerical patterns, yet precise forecasts remain difficult. Biological systems follow statistical trends, yet individual outcomes vary widely. Numbers provide insight and guidance, but they do not promise certainty. They outline possibilities rather than outcomes. What makes numerical patterns in nature compelling is not their precision, but their consistency. Similar structures appear across very different scales. Spirals in shells resemble spirals in galaxies. Branching in trees echoes branching in blood vessels. These similarities do not arise from shared design, but from shared constraints. When systems grow under similar pressures, similar solutions emerge. Energy efficiency, space optimization, and stability guide many natural processes. When growth follows these pressures, similar patterns appear again and again, not because nature aims for elegance, but because these forms work. Humans notice these recurring structures and describe them using numbers, yet the numbers themselves do not drive the process. They arrive afterward as descriptions rather than instructions. This is why mathematical models succeed when systems are constrained and repetitive, and struggle when systems are chaotic or sensitive to small changes. Numbers reveal tendencies, not guarantees. Nature tolerates variation. No two leaves are identical. No two waves break the same way. And this variability is not a flaw. It is resilience. Numbers help humans recognize structure without eliminating uncertainty. They offer insight rather than control. Nature behaves, humans observe, and numbers follow. Patterns feel mathematical, yet they remain physical. Numbers feel universal, yet they remain human. Between these two truths, understanding quietly grows. When humans began noticing that similar numerical patterns appeared in very different natural systems, curiosity deepened. Why should spirals appear in shells, storms, and galaxies alike? Why should branching structures repeat in trees, rivers, lungs, and lightning? These similarities suggested that nature was not producing random forms, but responding to shared constraints. Growth, flow, and distribution problems often lead to similar solutions, even in unrelated environments. One of the most striking examples appears in branching systems. Trees branch to distribute water and nutrients efficiently. Rivers branch to drain landscapes with minimal energy loss. Blood vessels branch to deliver oxygen throughout the body. In each case, the structure balances reach with efficiency. The exact measurements vary, but the proportional relationships remain recognizable. Humans later describe these patterns numerically, but the branching emerges naturally from physical necessity. Natural rhythms appear wherever movement, growth, or change exists. Ocean waves, sound waves, and even brain waves follow repeating cycles. Nature does not count these cycles, but their regularity makes them measurable. Concepts like frequency, amplitude, and wavelength are human tools used to describe motion that already exists. The same is true for growth. Many systems grow quickly at first, and then slow as resources become limited. This pattern appears in populations, bacterial cultures, forests, and even the spread of ideas. These behaviors can be described with curves and equations, but the processes themselves are biological or social. Numbers allow comparison and recognition, not causation. Time follows a similar logic. Day and night, seasons, and biological rhythms repeat often enough to be tracked, but they are never perfectly uniform. Humans divide these cycles into hours, days, and years for convenience, drawing clean lines over natural variation. Even randomness follows tendencies. Raindrops fall unpredictably, yet averages emerge. Mutations occur by chance, yet evolution shows direction. As science advanced, humans learned that numerical patterns describe how systems behave without explaining why. Modern technology reflects this understanding, favoring flexibility over precision. Buildings sway, bridges bend, systems allow error. Numbers no longer rule nature. They quietly guide how humans observe it, revealing structure without silencing uncertainty. At first glance, numbers appear calm and obedient. They line up neatly on the number line, follow clear rules, and behave exactly as expected. This is how most people encounter them in everyday life. Counting objects, measuring distance, checking time. In these contexts, numbers feel reliable and predictable. But as soon as humans began looking more closely, something unexpected appeared. Not all numbers behave the same way. Some refuse to fit comfortably into human intuition. The earliest signs of this discomfort appeared when mathematicians noticed that certain numbers resisted division. Most numbers can be broken down into smaller parts, but some cannot. These numbers are divisible only by one and themselves. Today, they are called prime numbers. They appear simple, almost humble, yet they hide one of the deepest mysteries in mathematics. Prime numbers do not follow a smooth pattern. They appear irregularly, sometimes close together, sometimes far apart. There is no simple formula that predicts exactly where the next prime will appear. Ancient Greek mathematicians noticed this unpredictability early on. One of them, Euclid, demonstrated that prime numbers never end. No matter how many are found, there will always be another. This discovery was unsettling. It suggested that infinity was not an abstract idea far removed from daily life, but something hiding inside basic counting. This idea quietly changed how numbers were perceived. Counting was no longer just about quantity. It revealed endless structure. The number line, once thought finite and manageable, became infinite and uneven. Numbers stopped feeling like tools and began feeling like territory. Not long after this realization, another shock followed. Some quantities could not be expressed as fractions at all. Early mathematicians believed that any measurement could be written as a ratio of whole numbers. This belief was deeply rooted in philosophy as much as mathematics. Harmony, balance, and order were thought to be numerical. Then the square root of 2 appeared. It described the diagonal of a square with sides of length 1. The value existed physically. The diagonal could be drawn, measured, and observed. Yet no fraction could represent it exactly. Its decimal expansion continued endlessly without repeating. This kind of number later became known as irrational. For followers of Pythagoras, this discovery was deeply disturbing. If numbers governed reality, and reality contained quantities that refused to be expressed cleanly, then numerical harmony itself was incomplete. The discomfort was not mathematical alone. It was philosophical. Numbers had revealed a crack in the idea that the universe was built entirely on perfect ratios. Around the same time, another strange absence became noticeable. There was no number for nothing. Counting systems included symbols for 1, 2, and many, but not for absence. 0 did not exist as a number. It was not seen as necessary. After all, how could nothing be something? This absence shaped entire civilizations. Roman numerals, for example, had no 0. This made certain calculations cumbersome and limited mathematical development. Without 0, there was no true place value system. Numbers remained tied closely to objects and quantities rather than abstract positions. Zero emerged slowly and reluctantly. In India, mathematicians began treating zero as both a placeholder and a number with its own behavior. It could be added, subtracted, and positioned. This idea was revolutionary. Zero allowed numbers to stretch infinitely in both directions. It made large calculations manageable and small differences visible. When zero traveled west through Arabic scholarship, it met resistance. Some Europeans believed it was dangerous or deceptive. A symbol representing nothing felt unnatural. Merchants using the new numerals were sometimes accused of fraud, yet the advantages were undeniable. Over time, zero became essential. It quietly transformed mathematics without asking for approval. Once zero was accepted, numbers became more flexible. Negative numbers followed. At first, they seemed impossible. How could a number be less than nothing? But real-world situations demanded them. Debt, loss, and direction all required quantities below zero. What began as an abstract idea became practical. Still, discomfort remained. Negative numbers existed, but they did not feel real. They were useful, but suspicious. This pattern repeated again and again. Numbers that initially felt absurd eventually became indispensable. Then came one of the most famous unsettling numbers of all, pi. At first, pi seemed simple. It arises from a circle, one of the most basic shapes humans know. Pi describes the relationship between a circle's circumference and its diameter. No matter the size of the circle, this ratio remains constant. But pi never ends. Its decimal expansion continues infinitely without repeating. No fraction can capture it exactly. Ancient civilizations worked with approximations. The Egyptians, Babylonians, and later Archimedes all developed methods to estimate its value. Perfection was impossible. Usefulness was enough. Pi revealed something important. Some numbers describe relationships rather than quantities. They are not about counting objects. They are about understanding structure. Pi cannot be written down completely, yet it governs everything circular, from wheels to waves. As mathematics expanded, more strange numbers appeared. Some numbers behaved well under addition, but strangely under multiplication. Others solved equations, but could not be visualized easily. Each new discovery challenged intuition. Perhaps the most unsettling of all were imaginary numbers. The square root of -1 made no sense in the traditional framework. How could a negative quantity have a square root? The term imaginary was not meant as an insult. It reflected confusion. These numbers did not fit into the known world. Yet imaginary numbers refused to disappear. They solved real problems. Over time, they became essential in engineering, physics, and signal processing. Electricity, waves, and modern computing rely on them. What once seemed absurd turned out to describe reality more accurately than familiar numbers could. Throughout this journey, one theme repeats. Human intuition lags behind numerical discovery. Numbers often behave correctly long before humans feel comfortable with them. Acceptance follows usefulness, not understanding. As these strange numbers accumulated, mathematics shifted. It was no longer about measuring land or counting goods. It became a study of behavior. Numbers were observed, tested, and explored much like natural phenomena. This shift changed the role of the mathematician. Instead of inventing rules, mathematicians began uncovering them. Numbers revealed properties that no one had designed. Patterns appeared unexpectedly. Proofs followed observation. What makes this unsettling is that numbers feel human, yet behave independently. They are discovered rather than created. Their behavior is consistent, but not always intuitive. They follow rules, but not necessarily the ones humans expect. As mathematical thinking deepened, numbers gradually stopped feeling neutral. Some followed familiar rules and behaved predictably, while others resisted simplification and challenged intuition. Counting ordinary objects did not prepare the mind for infinity, just as measuring distance could not explain why certain quantities could never be written exactly. Numbers revealed that they were more than measurement tools. They had their own internal logic. Even the most abstract of these numbers proved to be essential. Modern science, engineering, and technology rely on quantities that once seemed impossible or meaningless. Electricity, waves, and digital systems depend on numbers that cannot be pictured in ordinary space. Mathematics slowly shifted from something humans applied to the world into something they learned to navigate. Numbers did not change to suit human intuition. Human intuition adapted quietly to them. As numbers became more complex, mathematicians began to notice that the strange behavior of individual numbers was only part of the story. When numbers interacted with one another, even familiar rules could produce unexpected results. Simple operations like addition and multiplication behaved differently depending on the numbers involved. This raised a quiet but important question. Were mathematical rules universal, or did they depend on context? One of the earliest signs of this tension appeared in paradoxes. Certain logical setups produced results that felt correct step by step, yet impossible when viewed as a whole. These paradoxes were not mistakes in calculation. They exposed limits in intuition. Numbers could follow rules perfectly and still lead to outcomes that felt wrong to the human mind. Some problems resisted solution entirely. Equations were written carefully, logic was applied correctly, and yet no answer appeared. Over time, mathematicians began to accept that not every question framed in numbers has a solution. This was unsettling. It suggested that mathematics was not an all-powerful language, but a system with boundaries. Infinity played a central role in this realization. At first, infinity was treated as a distant idea, something that extended forever but never needed to be reached. Later, it became something that could be compared. Some infinities turned out to be larger than others. This discovery challenged the idea that infinity was a single concept and forced mathematicians to rethink size, quantity, and comparison. At the same time, probability began to reshape how numbers were understood. Instead of asking what will happen, probability asked what is likely to happen. This shift acknowledged uncertainty as a feature rather than a flaw. Numbers no longer promised exact outcomes. They offered ranges, tendencies, and expectations. This way of thinking transformed science. Physical systems could now be described statistically rather than deterministically. Heat, motion, and even matter itself began to be understood through averages and distributions. The behavior of individual particles became less important than the patterns formed by many. Chaos theory pushed this idea even further. Some systems followed precise rules, yet remained unpredictable over time. Tiny differences in starting conditions produced wildly different outcomes. Numbers could describe the system perfectly, yet long-term prediction remained impossible. Order and unpredictability existed side by side. Computation introduced another layer of complexity. With the rise of machines capable of performing millions of calculations per second, numbers began interacting at scales beyond human perception. Algorithms produced results that no single person could trace step by step. Mathematics became something executed rather than observed. This raised new questions about trust and understanding. If a result is correct, but cannot be fully followed by a human mind, what does understanding mean? Numbers continued to function reliably, even as human intuition lagged behind their speed and scale. Today, numbers quietly govern systems that shape daily life. They rank, predict, optimize, and decide. Yet beneath this authority lies the same pattern seen throughout history. Numbers behave according to their own logic. Humans learn, slowly, to interpret the results. In this way, numbers remain both familiar and strange. They feel solid and dependable, yet they continue to reveal limits, surprises, and unanswered questions. Their behavior has not become simpler. Humans have simply become better at living with the uncertainty they produce. Numbers did not only help humans understand the world. Over time, they began to organize it. Once quantities could be counted, compared, and recorded, they became tools for structure. Slowly, almost invisibly, numbers moved from observation into authority. They stopped describing reality and began shaping how reality was handled. One of the earliest places this shift became clear was time. Natural time does not arrive in neat segments. Day fades into night. Seasons blend into one another. Yet humans divided this continuous flow into hours, days, weeks, and years. These divisions feel ancient and inevitable, but they are inventions layered onto natural rhythms. Time itself does not move in hours. Humans decided where to place the lines. Early calendars reveal how difficult this process was. Lunar cycles did not fit cleanly into solar years. Months drifted. Festivals slipped out of alignment. To maintain order, societies adjusted time itself. Extra days were added. Months were reshaped. Calendars became compromises between observation and convenience. Numbers did not follow nature perfectly. Nature was bent gently to fit numerical frameworks. Once time was divided, it became manageable. Work could be scheduled. Rituals could be repeated. History could be recorded. A date fixed an event in memory. Numbers gave time edges, even though time itself has none. This created the comforting illusion that time could be controlled. The same pattern appeared with space. Distance in the natural world is continuous. There are no visible units between here and there, yet humans introduced measurements. Steps became lengths. Lengths became standardized units. Eventually, the meter, the mile, and the kilometer appeared. These units allowed space to be compared, traded, and planned. Maps accelerated this transformation. A map is not the territory it represents. It flattens hills, compresses distances, and simplifies complexity. But once space could be drawn and numbered, it could be managed. Borders became lines. Land became parcels. Numbers turned landscapes into systems. This simplification was powerful. It allowed cities to be planned, roads to be built, and empires to expand. But it also removed detail. Local variation disappeared. What could not be measured easily was often ignored. Numbers brought clarity, but at a cost. As numbers entered governance, their influence deepened. Populations were counted. Resources were tallied. Taxes were calculated. Censuses transformed people into totals. Once something could be counted, it could be managed. Once it could be managed, it could be controlled. This did not happen overnight. Early counts were rough and incomplete. But even approximate numbers changed how leaders thought. Decisions were no longer based solely on stories or impressions. They were justified by figures. Numbers carried authority because they appeared neutral. Economics strengthened this shift. Value, once tied to objects or labor, became abstract. Coins standardized worth. Prices reduced complex exchanges into simple comparisons. Later, paper money and digital balances pushed value even further from physical reality. A number came to represent trust. Debt introduced a further abstraction. Owing something meant holding a negative quantity. This required numbers to describe absence, obligation, and future commitment. Interest rates added time into the equation. Numbers now governed not only what existed, but what was promised. Markets responded to numbers quickly. Prices fluctuated, ratios changed, trends emerged. Over time, numerical indicators replaced direct experience. A rising number suggested growth. A falling one suggested danger. The underlying reality could be complex, but the number felt decisive. Statistics amplified this effect. Instead of tracking individuals, large groups could be summarized. Averages replaced stories. Trends replaced anecdotes. This made large-scale understanding possible. It also blurred individual experience. The concept of the average person emerged. No one actually is the average, yet the idea became influential. Policies were designed around averages. Systems were optimized for typical cases. Outliers became invisible. Numbers smoothed reality. This smoothing was both useful and misleading. It allowed patterns to be seen, but it hid variation. Averages concealed extremes. Totals masked distribution. Numbers told a story, but not the whole one. Despite this, trust in numbers grew. Figures felt objective. They seemed immune to bias. The numbers don't lie became a common belief. Yet numbers only reflect what is measured and how it is measured. Choices are always involved. Measurement requires decisions. What to count, what to ignore, where to draw boundaries. Two measurements of the same phenomenon can tell different stories. Numbers appear precise, but they depend on context. This tension becomes especially visible in risk and probability. Numbers can describe likelihood, but they can never guarantee outcomes. A low probability event can still occur, and a high probability outcome can still fail. Numbers do not remove uncertainty from the world. They simply give uncertainty a shape that can be discussed, compared, and acted upon. As societies began relying more heavily on numerical systems, confidence slowly grew. Planning became more ambitious. Projects expanded, and predictions reached further into the future. Numbers made large-scale coordination possible. Infrastructure, trade networks, and communication systems depended on numerical precision, and without it, modern life could not function in its current form. At the same time, numbers gradually became invisible. Units, prices, schedules, rankings, and scores faded into the background of daily life. People followed them without actively noticing them. Numbers stopped feeling like tools and began to feel like the natural structure of reality itself. This invisibility made numbers especially powerful. When something is taken for granted, it is rarely questioned. Numerical systems shaped behavior quietly. Deadlines created urgency, scores created competition, and rankings created hierarchy, often without anyone consciously deciding that they should. Even identity began to take numerical form. Age, income, ratings, and performance metrics became ways people described themselves and others. Success and failure gained measurable definitions. Worth became something that could be compared, tracked, and improved over time. Yet something unresolved remained beneath this order. Numbers brought structure and clarity, but they did not bring meaning. They explained how much, how often, and how likely, but they never explained why. Experience was simplified, but never fully captured. This gap is where quiet tension lives. Humans rely on numbers to navigate complexity, yet continue to sense that something essential is missing. Precision does not equal understanding, and control does not equal wisdom. Numbers organize the world effectively, but the order they create is real without being complete. As numbers became more deeply embedded in decision-making, a subtle shift occurred. They were no longer just tools for organizing reality. They began to stand in for reality itself. When a situation could be reduced to a number, that number often became more influential than the situation it represented. What could not be measured slowly lost importance. This shift is especially visible in modern institutions. Schools, workplaces, and governments rely heavily on numerical indicators. Grades, scores, rankings, and performance metrics promise fairness and objectivity. They allow large systems to function efficiently, but they also compress complex human experiences into simplified signals. A single number can overshadow years of context. In medicine, this tension appears in seemingly precise measurements. Blood pressure, heart rate, and risk percentages guide decisions, yet they never describe a full human body. Two people with identical numbers can experience very different outcomes. Numbers support judgment, but they cannot replace it. When treated as absolute truth, they create blind spots. The same pattern appears in economics. Gross domestic product, inflation rates, and market indices summarize vast systems into compact forms. These numbers are useful, but they privilege certain kinds of activity while ignoring others. Care, rest, environmental damage, and long-term well-being often disappear because they are difficult to quantify. What is counted feels real. What is not counted feels invisible. Probability adds another layer of complexity. Risk assessments express uncertainty in numerical form, which creates a sense of control. A percentage feels concrete, even when it describes something deeply uncertain. People often mistake likelihood for fate. When outcomes differ from expectations, trust in numbers weakens, even though the numbers never promised certainty. This misunderstanding is amplified by averages. Averages describe groups, not individuals, yet they are frequently applied as if they describe everyone equally. An average income, an average lifespan, or an average risk hides variation. Most people do not live at the average. They live at the edges, where numbers become less informative. Algorithms intensify this effect. Decisions once made by humans are increasingly guided by automated systems that operate entirely on numbers. These systems optimize efficiency, predict behavior, and rank importance. Their logic is consistent, but their assumptions are often invisible. Bias enters not through malice, but through what is chosen to be measured and what is ignored. Over time, people adapt to these systems. Behavior changes to fit metrics. Actions are shaped by what improves scores, rankings, or visibility. This feedback loop reinforces the power of numbers. The measurement begins to influence the thing being measured. Yet even as numbers grow more dominant, their limitations remain. Unexpected events disrupt forecasts. Outliers break models. Human behavior resists full prediction. Each failure reveals the same truth from a different angle. Numbers are powerful guides, but fragile rulers. This fragility does not make numbers useless. It makes them human. They reflect choices, values, and priorities. They show what a society cares enough to measure. In this way, numbers quietly reveal culture as much as they organize it. Understanding this does not require rejecting numbers. It requires listening to them carefully. Numbers speak clearly about quantity and pattern, but they are silent about meaning. They can inform decisions, but they cannot decide what matters. And so humans continue balancing trust and doubt when it comes to numbers. They rely on them to navigate complexity, to reduce uncertainty, and to make large systems manageable. Numbers offer clarity in moments that would otherwise feel overwhelming. They allow comparison, prediction, and coordination on a scale no individual mind could handle alone. In this sense, numbers are not cold or distant. They are deeply practical companions. At the same time, humans gradually learn that every measurement leaves something behind. Reality always exceeds its numerical outline. What is measured becomes visible, but what resists measurement quietly fades from view. Emotions, intentions, long-term consequences, and subtle differences rarely fit neatly into numerical form. They remain present, shaping outcomes, even when they are not counted. The order numbers create is real, but it is partial. It simplifies so that action becomes possible. Without this simplification, many decisions would stall entirely. Yet simplification comes with trade-offs. When numbers become the primary lens, nuance is compressed and complexity is flattened. What feels precise may still be incomplete. This is why numbers often feel both reassuring and unsatisfying. They provide answers, but rarely explanations. They describe patterns, but not meaning. They tell us how much, how fast, how likely, but remains silent about why something matters in the first place. That silence is not a flaw. It is a boundary. Learning to live with numbers means learning to hear both what they say and what they leave unsaid. It means using them as guides rather than substitutes for judgment. Numbers work best when they inform human understanding, not when they replace it. Between trust and doubt, between clarity and uncertainty, this quiet balance continues to shape how numbers are used, believed, and lived with every day. Numbers feel precise. They arrive with clean edges, clear meanings, and a promise of certainty. When a situation is reduced to a number, it often feels easier to understand, easier to trust. Yet this sense of clarity hides an uncomfortable truth. Numbers are not misleading on their own. The human mind is. The gap between numerical accuracy and human interpretation is where confusion quietly begins. The human brain did not evolve to understand large quantities. It evolved to survive in small groups, in immediate environments, with limited resources. For most of human history, the difference between 3 and 4 mattered. The difference between 1,000 and 1 million did not. This evolutionary history still shapes how numbers are felt today. Small numbers are intuitive. We recognize them instantly. 3 objects on a table require no counting. 4 feels different from 5. This ability is fast and reliable. But as numbers grow larger, intuition fades. 1,000, 1 million, and 1 billion stop feeling distinct. They become abstract labels rather than lived quantities. This is why statements involving large numbers often fail to create understanding. 1 million seconds is about 11 days. 1 billion seconds is more than 30 years. Yet when people hear the numbers alone, they often feel similar. The mind registers very large and moves on. Scale disappears. This limitation affects decision-making constantly. Budgets, populations, distances, and risks are often discussed using numbers far beyond intuitive reach. Without concrete reference points, the brain fills the gap with emotion rather than understanding. A large number can feel either terrifying or meaningless, depending on context. Probability introduces a second layer of difficulty. Human intuition struggles with uncertainty expressed numerically. Percentages feel precise, yet they describe tendencies rather than outcomes. A 1% chance sounds small, but it does not mean impossible. A 99% chance sounds safe, but it does not mean guaranteed. This mismatch leads to predictable errors. Rare events are often ignored until they happen. When they do, they feel shocking, even if they were always possible. At the same time, common events are often treated as inevitable, even when they are not. Numbers describe likelihood, but the mind hears certainty. Gambling reveals this clearly. Players understand the odds intellectually, yet behave as if chance has memory. After a series of losses, a win feels due. This belief has no mathematical basis. Each event is independent, but the brain seeks patterns, even where none exist. Insurance decisions show a similar pattern. People often underestimate everyday risks and overestimate traumatic ones. Rare but vivid events receive attention, while common but dull risks are ignored. Numbers may be accurate, but emotional weight reshapes interpretation. Percentages add another layer of confusion. A 50% increase sounds dramatic, but without context, it means little. An increase from 2 to 3 is a 50% change. An increase from 200 to 300 is also 50%. The number hides the scale. Ratios behave the same way. A small change in a small system can appear large. A large change in a large system can appear modest. Without absolute values, percentages can mislead without lying. They compress stories into symbols. Averages further complicate understanding. The idea of the average person feels natural, yet such a person rarely exists. Averages smooth variation, hiding extremes. In income, health, or performance, most individuals live far from the average. Yet policies and expectations are often built around it. This creates quiet distortions. When people compare themselves to averages, they may feel inadequate or falsely secure. The number feels authoritative, even when it represents no one in particular. The average becomes a phantom standard. Time estimates suffer from similar errors. People consistently underestimate how long tasks will take. This is not random optimism. It is a systematic bias. The brain recalls best-case scenarios more easily than typical outcomes. Numbers promise control, but memory reshapes them. Even experts are not immune. Studies show that professionals in many fields make predictable numerical errors when relying on intuition. Experience does not remove bias. It often reinforces confidence without correcting perception. Graphs and charts, designed to clarify, can deepen confusion. Visual representation adds another interpretive layer. Small changes can be exaggerated or minimized depending on scale. The eye trusts shape before reading numbers. A rising line feels dramatic, even when the change is modest. The starting point of a graph matters. A truncated axis can make stability look volatile. A stretched axis can make dramatic change look calm. The numbers remain accurate. The interpretation shifts. Frequency and probability are often confused. Hearing that something happens often does not mean it is likely. Media coverage amplifies rare events, making them feel common. Repetition replaces statistical reasoning. Emotion plays a powerful role in all of this. Fear, hope, and loss distort numerical thinking. The same number feels different depending on emotional context. A loss of $100 feels larger than a gain of the same amount. This asymmetry is built into human psychology. This is why numbers alone rarely change minds. Facts presented without emotional framing often fail to persuade. The mind does not process numbers in isolation. It embeds them in stories, expectations, and identity. Over time, people develop personal rules of thumb. These shortcuts simplify decision-making, but introduce consistent errors. They feel efficient, yet they trade accuracy for comfort. Numbers become suggestions rather than signals. Modern life intensifies these effects. People encounter more numbers than ever before. Scores, metrics, notifications, statistics. The volume overwhelms attention. To cope, the mind simplifies further. Meaning is replaced by reaction. This creates an illusion of numerical literacy. Numbers are everywhere, but understanding remains shallow. Familiarity is mistaken for competence. The presence of data feels like knowledge. Yet the patterns of error remain stable. Humans misjudge scale, probability, and risk in predictable ways. These mistakes are not signs of failure. They are features of cognition shaped by evolutionary constraints. Understanding this does not require rejecting numbers. It requires humility. Numbers are powerful tools, but they do not bypass human limits. They work best when paired with context, explanation, and reflection. As numbers continue to guide decisions in medicine, finance, technology, and policy, this gap matters more than ever. The danger is not that numbers are wrong. It is that they are believed without being understood. This tension does not disappear. It repeats quietly each time a decision is made, a risk is taken, or a forecast is trusted. Numbers remain precise. The mind remains human. And this is where the quiet mystery deepens. Not in the numbers themselves, but in how confidently humans misread them. One of the most surprising things about numerical mistakes is how consistent they are. People do not misunderstand numbers randomly. They tend to make the same errors again and again across cultures, education levels, and professions. This predictability has led researchers to study numerical bias not as a failure of intelligence, but as a feature of human cognition. One such bias appears when numbers are framed differently. A medical treatment described as having a 90% survival rate feels safer than one described as having a 10% mortality rate, even though the information is identical. The numbers do not change, but the emotional framing does. The mind reacts to language before it processes equivalence. Another common distortion appears in loss aversion. People tend to feel losses more strongly than gains of the same size. Losing $100 produces more discomfort than gaining $100 produces satisfaction. This imbalance affects financial decisions, risk-taking, and long-term planning. Numbers remain equal, but their psychological weight does not. Time adds another layer of distortion. Humans heavily discount the future. A benefit promised years from now feels less real than a smaller benefit available immediately. This is why saving money, reducing long-term risk, or investing in prevention feels difficult, even when numbers clearly support it. The future is translated into smaller emotional value. Confidence further complicates interpretation. When people feel confident, they rely more on intuition and less on calculation. This often leads to errors, especially with probability and scale. Ironically, increased familiarity with numbers can sometimes increase mistakes by encouraging shortcuts instead of careful reasoning. Anchoring is another powerful effect. When an initial number is presented, it influences all later judgments, even if it is irrelevant. A price suggestion, an estimate, or a statistic becomes a reference point. Subsequent decisions drift around that anchor rather than starting fresh. The first number heard quietly shapes perception. Comparisons also mislead. Numbers rarely appear alone. They are compared to previous values, expectations, or social norms. A salary feels high or low depending on context. A risk feels acceptable or frightening depending on what it is compared against. Numbers gain meaning relationally, not absolutely. Scale blindness becomes especially visible with exponential growth. Linear intuition fails when growth accelerates. Processes like population increase, viral spread, or compound interest feel slow at first and then suddenly overwhelming. The math is correct throughout, but intuition lags behind reality. This lag explains why warnings are often ignored until effects become obvious. Early numbers feel small and manageable. By the time growth becomes visible, intervention is harder. This pattern repeats across public health, finance, and environmental systems. Another source of error comes from mixing categories. People often combine unrelated numbers into single judgments. Risk, cost, benefit, and probability blur together. A decision feels right or wrong based on an overall impression rather than careful separation of variables. Over time, repeated exposure to numbers can create fatigue. When faced with too many statistics, the mind disengages. Numbers lose meaning and become noise. In this state, people fall back on emotion, habit, or authority, even when numerical information is available. Experts are not immune to these effects. Specialization improves calculation skill, but it does not eliminate bias. Professionals often perform better with familiar problems and worse with unfamiliar framing. Expertise changes the shape of error, not its existence. Understanding these patterns does not make mistakes disappear, but it changes how numbers are approached. Instead of expecting intuition to be reliable, systems can be designed to slow decisions, add context, and reduce distortion. Awareness does not grant immunity. It grants caution. Numbers remain essential guides, but they require interpretation that respects human limits. When treated as final answers, they mislead. When treated as signals within a broader understanding, they inform. The difference lies not in the numbers themselves, but in how quietly and carefully they are read. Numbers did not suddenly take control of modern life. They arrived quietly, through convenience rather than force. One by one, small decisions were handed over to numbers because they seemed faster, clearer, and more reliable. Over time, this accumulation changed how the world functions. Numbers stopped assisting decisions and began shaping them. Today, many choices are no longer made directly by people. They are guided by systems that translate human behavior into numerical signals. Preferences become data points. Actions become patterns. Once behavior can be counted, it can be predicted. Once it can be predicted, it can be optimized. This shift is most visible in algorithms. An algorithm is not intelligent in a human sense. It does not understand meaning or intention. It follows rules applied to numbers. Yet these systems increasingly decide what people see, hear, read, and are offered. They do not need to know who someone is. They only need to recognize numerical similarity. Recommendation systems work this way. They compare behavior across millions of users, identify patterns, and suggest what is statistically likely to keep attention engaged. The individual experience feels personal, but it is generated through comparison. A person becomes a cluster of probabilities rather than a unique story. This changes how choice feels. When options are filtered before they are seen, freedom becomes subtle. People still choose, but they choose from what remains. Numbers quietly shape the landscape of possibility. Scores and rankings reinforce this effect. Social platforms, search engines, and marketplaces rely on numerical ordering. Items at the top receive attention. Items below fade into obscurity. Visibility becomes a numerical outcome rather than a qualitative judgment. This logic extends beyond digital spaces. Credit scores influence financial access. Test scores influence education paths. Performance metrics influence employment. In each case, a complex human profile is compressed into a single value. The number travels faster than the story behind it. These systems promise fairness by removing human bias. Numbers appear neutral, but neutrality depends on what is measured. If a system values speed over care, productivity over depth, or consistency over creativity, those priorities become embedded in its outcomes. Numbers do not remove values. They encode them. As these systems spread, behavior adapts. People learn how numbers work and adjust accordingly. Content is shaped to perform well in rankings. Work is structured to meet measurable targets. Decisions are optimized for metrics rather than meaning. This feedback loop strengthens numerical influence. The measurement changes behavior. The changed behavior reinforces the measurement. Over time, the system feels natural, even inevitable. Time management reflects this shift. Productivity tools break the day into units. Tasks are tracked, timed, and scored. Efficiency becomes a goal in itself. Rest, reflection, and unstructured thought struggle to find space because they resist measurement. Even attention becomes numerical. Minutes watched, clicks made, interactions counted. Platforms optimize for engagement without understanding satisfaction. A system can maximize attention while minimizing well-being. The numbers do not reveal this difference unless it is measured explicitly. Health offers another example. Wearable devices track steps, heart rate, sleep cycles, and activity levels. These metrics can be useful. They offer insight into patterns that might otherwise go unnoticed. But they also change perception. Well-being becomes a dashboard. Two people with identical health numbers can feel very different. Numbers inform, but they do not replace lived experience. When metrics dominate attention, subtle signals may be ignored. Education follows a similar pattern. Learning is reduced to grades, rankings, and standardized scores. These measures allow comparison across large groups, but they struggle to capture curiosity, resilience, or depth of understanding. Students learn what is rewarded numerically. In workplaces, performance reviews increasingly rely on measurable outcomes. Sales figures, response times, output counts. Collaboration, mentorship, and creative problem-solving often resist easy measurement. What cannot be counted risks being undervalued. This creates a quiet shift in motivation. People optimize for visible success. Invisible contributions fade. Numbers shape what feels worth doing. Even culture adapts. Music, writing, and art are filtered through metrics. Plays, views, likes, and shares influence what is produced. Popularity becomes a proxy for value. Algorithms reward repetition and familiarity because they perform well numerically. This does not eliminate creativity. It channels it. Risk becomes costly when numbers punish deviation. Familiar patterns feel safer when metrics reward predictability. Despite this, numbers also enable connection at scale. They allow systems to function that would otherwise collapse under complexity. Logistics, communication, medicine, and science depend on numerical precision. Modern life would be impossible without it. The issue is not presence, but dominance. When numbers become the primary language of decision-making, other forms of understanding struggle to compete. Qualitative judgment feels slow. Context feels inefficient. This tension appears most clearly when systems fail. Unexpected events reveal assumptions hidden inside numbers. Models break. Predictions miss. What was treated as stable reveals fragility. When this happens, trust wavers. People question the numbers, not because they are wrong, but because they were asked to do too much. Numbers can guide, but they cannot replace interpretation. Modern systems often forget the boundary between measurement and meaning. Numerical authority is extended into areas it cannot fully capture. Human behavior, emotion, intention, and context resist complete quantification. When numbers are asked to represent these things alone, something essential is lost, even if the system continues to function smoothly. Despite this limitation, numbers continue to expand their reach. Artificial intelligence systems learn entirely from numerical data. They detect patterns, correlations, and statistical regularities without understanding cause or intention. Their outputs feel intelligent because they align closely with human behavior, not because they comprehend it. This creates a new kind of distance between decision and responsibility. Choices are increasingly shaped by systems no single person fully understands. When outcomes are questioned, accountability becomes unclear. The authority shifts quietly from people to numbers, from judgment to output. Yet humans are never truly outside these systems. They design them, train them, and decide what data is included or excluded. Every measurement reflects a choice. Every metric carries a value, even when it appears neutral. The quiet power of numbers is always rooted in human priorities, whether visible or hidden. Recognizing this relationship changes how numbers are perceived. They are not external forces imposing control from the outside. They are mirrors reflecting collective decisions about what matters. What a society chooses to measure reveals what it chooses to value. This awareness does not require rejecting numerical systems. It requires restraint. Numbers are highly effective tools, but they function best within limits. They support judgment, but they cannot replace it. Without reflection and context, numerical clarity becomes shallow. Modern life depends on numbers at every level, yet it is not defined by them alone. Between metrics and meaning lies a space where human experience still operates. This space includes empathy, uncertainty, creativity, and interpretation. It cannot be fully measured, but it can be acknowledged and protected. As numbers continue to guide modern systems, this balance grows more important. Efficiency must coexist with care. Precision must coexist with humility. Measurement must coexist with understanding, or the system begins to mistake control for insight. Numbers will continue running quietly beneath daily life. They will schedule, rank, predict, and optimize without drawing attention to themselves. The question is not whether they should exist, but how consciously they are used. For now, noticing their presence is enough. Recognizing when a number is informing a decision and when it is silently making one restores a measure of agency. Awareness does not remove numerical influence, but it gives it boundaries. Within those boundaries, modern life continues. It is shaped by numbers that rarely announce themselves, yet touch almost every moment, quietly influencing how the world is organized, experienced, and understood. As numbers quietly take on more responsibility, they begin to shape not only systems, but expectations. People adjust their behavior to fit what is measured, often without realizing it. When success is defined numerically, effort flows toward what improves the number rather than what improves the experience. Over time, this changes what feels worthwhile. In digital environments, this effect becomes especially subtle. Platforms learn which actions produce measurable engagement and gently guide users toward them. Attention becomes a resource to be optimized. Time spent, clicks, pauses, and returns are all counted. The system does not ask whether the experience was meaningful. It only registers that it held attention. This creates a quiet feedback loop. What performs well numerically is shown more often. What is shown more often becomes familiar. Familiarity feels comfortable, and comfort reinforces engagement. Without intention or design, numbers slowly narrow the range of what is seen and heard. The same pattern appears in decision-making systems. Automated recommendations influence what people buy, watch, read, and believe. These systems do not decide what is best. They decide what is statistically likely to continue interaction. The result feels efficient, but it also feels invisible. As numerical guidance increases, personal judgment is not removed. It is redirected. People still choose, but they choose within boundaries shaped by metrics. Freedom remains, but it is filtered. This filtering is rarely experienced as restriction because it operates quietly and consistently. Over time, trust shifts. Instead of trusting intuition, memory, or experience, people learn to trust the output. A score feels safer than a feeling. A rating feels clearer than a story. Numbers promise neutrality, even when they reflect hidden assumptions. This reliance changes how uncertainty is tolerated. When systems offer predictions, unpredictability feels like failure. When outcomes differ from expectations, frustration grows. The discomfort is not with uncertainty itself, but with the loss of numerical reassurance. Yet uncertainty has never disappeared. It has only been managed. Numbers reduce complexity enough to allow action, but they never eliminate chance. Unexpected events, human variability, and long-term consequences continue to escape full measurement. At their best, numbers function as quiet companions. They support decisions, reveal patterns, and extend human capacity. They help coordinate efforts across time and space. They make modern life possible without demanding constant attention. At their limit, numbers begin to act as substitutes rather than supports. Measurement slowly replaces reflection, and optimization takes the place of understanding. Decisions become faster, smoother, and easier to justify, yet they often feel thinner. Experience is streamlined into metrics that capture performance but miss texture. What can be counted moves forward quickly, while what resists measurement quietly falls behind. Life continues to run efficiently. Tasks are completed, systems function as intended, and outcomes appear clear. Yet something subtle fades into the background. The differences between moments, the reasons behind choices, and the emotional weight of outcomes are flattened into outputs that look complete, but never fully are. What remains is a surface of clarity that hides the depth beneath it. Between usefulness and reduction lies a fragile balance that is constantly negotiated. Numbers will continue to guide modern life, silently and effectively, because they are too practical to abandon. The question is not how to remove them, but how to remain awake to their influence. When numbers are used as instruments, they extend human capacity. When they become instructions, they narrow it. Leaving space for what cannot be counted does not weaken systems. It grounds them. Meaning, judgment, and human presence remain, quietly shaping the world alongside the numbers that try to describe it.